All right, so this is what we're going to cover in this chapter. Chapter 1, chemistry and chemicals. You're going to learn a lot about that, scientific method, how scientists think, and we really like to impress that upon you because that's very important in healthcare professions and things. How do you think through the process? And this is what we go through, and this is law for chemists. Learning chemistry. We'll talk a little bit about some study plans. We really won't talk much about that. I would do this as we go. So this section here, I think I completely pulled out of these slides. Math skills. We will be doing math skills. But we won't necessarily be stopping all the time doing them. We will be doing them. That's why you have those sheets. We'll be practicing, working through them until our math skills are sharpened. That's how we'll do the math skills. So we'll go through some, but we won't go into detail. We'll use worksheets to practice doing it. At the end of the day, many of the things you'll learn, I'm going to be teaching you how to do them. That's going to be a big part of what you're going to learn, how to do this, okay? How to think about it and how to do it, all right? Some of the rules, you're going to spend time memorizing those rules because someone told you to memorize all those rules. I'm going to also show you how to cut through memorizing those rules because at the end of the day, I'm not going to ask you to regurgitate to me what step you're on. Are you on step 1, 2, 3, 5, 6, 7, 8, 9, 10, 11? I'm not going to ask you that. If you perform, I'm going to assume you know the rules. So that's what I'm going to teach you how to do. Follow? All right? So, scientific notation and lots of math, we're going to do all of that. All right? Chemistry is the study of substances in terms of this composition, structure, properties, and reactions. If it's in bold, I expect you to memorize it. These are the types of definitions that we would expect you to know. So if you see it in bold, that's the definition. We expect you to memorize it. Composition, again, you have to learn the language. Okay? So let's not think about it as, I don't know chemistry. What I'm asking you to do is learn the language of chemistry. Follow? That's what we're asking you to do in this part. And for the most part, chapter 1 does a lot of that, of learning the language. So that's what we're going to be asking you to do. So I suggest you write these definitions a lot of times until we learn the language. Composition, what it's made of? Well, you can ask what's it made of. I'm going to ask you what's the composition. Okay? And so you'll need to know what's it made of. So if I ask you the composition of, for example, if I ask, what's the composition of, everybody always says it's CO2. Carbon dioxide, dry ice, the smoke at Beyonce's concert or Tim McGraw's concert. That's what it is, carbon dioxide, the stuff in the fire extinguisher. If I ask you what's the composition, you tell me carbon and oxygen. Okay? That means that's what it's made of. What's the structure? Its structure is how it's connected together. And in this case, it's connected like this. That's the structure. That's what it looks like. So composition, what's it made of? Structure, how is it put together? Where are they connected? In this case, we have carbon and we have 2 oxygen. And they're bonded to the central carbon. Properties, in this case, dry ice is sublimes. That's why it turns to smoke when you see it on the stage, when they put the water in it. It goes directly from a solid into its gaseous state. And that's why it does what it does. That's why it's so cool, because it creates the gas with all these particles. Okay? And reaction. Well, the reaction of carbon dioxide with water, it basically turns it into an acid. So we have reactions. So how do they behave? So these are the things we think about when we think of chemistry. And this is very important. For example, if you're a nursing major and your grandma's in the hospital, what medicine is grandma going to get? What's the composition of that medicine is very important. And this is when they talk about medicine, they talk about interactions of medicines and don't take certain medicine with the others because of reactions. How do they behave in the presence of other materials? What are the properties of this? What are characteristics and how does it do it? This is why these concepts are so important, and this is the language of chemistry that you already know, but we're asking you to learn it and say it in these terms. Why? Because this is our universal language. This is how one doctor talks to the other. This is how one scientist talks to the other around the world. Okay? And even in space. The field of chemistry is divided into these areas of chemistry. General chemistry, which is what you're taking. So general chemistry goes across the area and talks a little bit about all of it. But the basis of general chemistry is the basic fundamentals. It's kind of the ground. It's kind of the groundwork work. It's where you learn the basic principles, and that's what you will be learning. But in general chemistry, you will have an opportunity to experience a little bit of most of these chemistries in some fashion. Organic chemistry is carbon and hydrogen chemistry. It is this chemistry of life. It is the chemistry of your body. Your body's carbon, mostly carbon, hydrogen, and oxygen, with a little bit of phosphorus and nitrogen thrown around, and occasionally you get some sulfur in there, and you get other types of minerals and other elements. But organic. Biochemistry is that organic chemistry of biology. So you have organic chemistry that's biology, therefore we call it biochemistry. Then we have geochemistry, looks at the earth, okay, and what's happening there. And physical chemistry is chemistry of interactions. For example, there are some people who really can't stand to touch things, certain foods. You say, just touch your food. They can't touch it. It just bothers them. They can't touch certain surfaces. That's because of physical chemistry. There's something called tactile that annoys them. And for example, there are other people who like the taste of certain foods but don't like the taste in that form. That's because of the physical chemistry. The way it interacts in their mouth, they just cannot, it doesn't feel good. It doesn't taste good. And there, you'd say, well, it really probably doesn't feel good, is why you say it doesn't taste good. That's physical chemistry. Okay? And so that's what we have there. All right, so these are the branches of chemistry that we expect to expose you to and for you to be familiar with. Yes, you do well to memorize these. These are simply examples. We won't hold you to these examples, but chemicals or substances that have all types of composition and properties. We show examples here, soaps and lotions. There's chemistry there, toothpaste, cosmetics, clothes. They all have some form of chemistry. You're sitting on chemistry now. You're interacting with chemistry. You're breathing in chemistry, 78% nitrogen and 21% oxygen and about 1% of other gases. You inhale that and you exhale less oxygen. You burn it, combust it, carry out respiration, and it's converted to carbon dioxide, and that's chemistry. You eat a Snickers bar, and that's converted. That's carbon and hydrogen converted to, if it burns well, carbon dioxide and water. And by the way, if your child eats sugar, sugar does not make them hyper because it does not combust to any materials that will do that. It makes them happy to get a lollipop, but it doesn't make them hyper. Sugar doesn't do that. It doesn't have any of those types of organic molecules in them. Yes, that was my soapbox. Chemistry in our lives, all around us. You get it? That's the point we're trying to make. So you're starting to think like that. You're starting to see chemistry. Okay? All right? All right? So you follow? All right. So all around you, if you're touching it, you're feeling it, you're interacting with it. If you chew gum, chemistry. You get it? All right? You put on mascara, chemistry. You dye your hair. If you still have hair, chemistry. Okay? And of course, our good friends, plastics, chemistry, and don't forget, recycle. The scientific method, let's talk about it. The scientific method is a set of general principles that helps to describe how scientists think. This is the brain of the chemists. This is how they think about it for consistency of solving problems, or at least investigating the problems, even though in many instances we can't solve them. It is important that you understand all problems cannot be solved within the time frame that are useful to you. Okay, but they can all be investigated. And when we investigate for the purpose of solving problems, we investigate it using the scientific method. When we're in the laboratory, we use the scientific method. Okay? So, scientists make observations in chemistry laboratories, and you're here in Midland, Michigan. Yep, we're Dow. It used to be Dow Corning. Now it is purely all Dow. So you guys are at least familiar with that if you're anywhere in the Tri-City area. So let's look at the method. These are statements you want to memorize, and as we think about them. The scientific method involves observation, simply observing things. Facts obtained by observing and measuring events in nature. That's important. Facts obtained by observing and measuring events in nature. Okay? It is not something you make up. The tree is green. It blooms, and the flower blooms every spring. In the fall, the leaves turn brown. These are things you observe. Okay? If you eat a lot of Taco Bell, you gain weight. Okay? So, observing and measuring the events. Okay? A hypothesis statement that explains the observation. My clothes are getting smaller. Probably not, because I measured them, they're still a 42. Okay, they're a 45. Okay, 62, whatever they are. Okay? All right? They stayed the same. I put the same tape measure on me. Oops, I'm not a 64 anymore. I'm a 72. You get it? So a statement to explain the observation might be, in the last few months, I changed my eating habits, or I may be on medications to do whatever. You get it? So it's a matter of thinking about what's the hypothesis that could be leading to it. Could be wrong, could be right. Okay? In my case, my answer is always the same. I stopped going to the gym. Okay? All right? A hypothesis. Okay, it's a hypothesis. So I test that hypothesis by going back to the gym. That's the experiment. You run the procedure. Okay? I stayed away from Taco Bell. I went back to the gym, etc., etc. By the way, I just use examples. Okay? A theory, a model that describes how observations occurred using experimental results. So you have a theory about it. Okay? All right? I have a theory that the gray hair in my head is not due to my frustrations, because I'm never frustrated. It must be due to my birthdays. Okay? Some theory. Okay, so everyone follow. This is how we think, and this is how you'll be thinking. Okay? All right? What I don't want you to do is memorize these so hard that you don't think about what they mean. So everyone follow. Think about what they mean, not just memorizing them. Challenge yourself with examples. And here's how we do it. Some observations lead to direct laws. If I touch the stove, I will get burned. That is a law. Okay? All right? This is one, as soon as a kid touches it, get burned. And many times you say, no, it's hot, don't touch. It's a law. So the child takes it as a law. Okay? And they believe that law. For example, here's a very practical example of a law. My first son will only buy toys in the store at Meijer that cost 99 cents. Dad taught him that the best toys, best trucks to buy cost 99 when he was a kid. When he started older, he said, Dad, you really had me believing that too. Okay? It was law. Okay? He would see another toy and he would read it. He would see $3.90 something. He said, can't buy. And he'd go, 99. Good boy. That's what a law is. You get it? Okay? That's what, when we establish a law, that's it. It's established. And you function by the law. Okay? And you use that law to guide the actions. If you have high blood pressure, then you take these meds. You don't take ibuprofen. Get it? Okay, you take atenolol or something. You get it? That's an established now law. Okay? If your kidneys are not functioning and you want to live with a certain quality of life, you do dialysis. That's a law. Okay? And some of those are direct laws. Don't have to think about them. Don't take it through the process. Okay? It's here. All right? So we have this observation. So we have a hypothesis about this observation. Observation. The kids are getting sick. Hypothesis. Maybe we need to give them a med to prevent that. Let's try giving them vaccinations and see how that works. We observed that the numbers went down. Therefore, we come to the conclusion that these vaccinations are helpful based upon the way they work. They work by these principles, okay? And since they're there, it becomes a conclusion and a theory. And we say, wait a minute, we're going to establish that as a law, as a rule. Follow? So this is how we take it through the process. And this is how we'll be challenging you to think through problems. We'll hopefully give you some problems to help you do this, okay? This is how we do the scientific method, okay? So here we are. Here's an example of observation. Yesterday we went to visit a friend. Soon after we arrived, your eyes began to itch and start to sneeze. You observe the friend has a new cat. That's simply an observation. You're sneezing. We just use an example, and we'll move through this quickly. Perhaps you're allergic to cats. Maybe. Okay? Could be allergic to the cat owner. That's a different story. All right? Perhaps you're allergic to cats. Okay, experiment 1. Test your hypothesis. You leave the friend's home. If it stops, perhaps the hypothesis is correct, but you don't know that for sure, right? If the itch and the sneeze does not stop, perhaps it's a cold. So you have an option. Allergy is a cold. And so that's how you make it. While leaving your friend's home, the itch stops. Observation supports your original hypothesis, confirming you visit another friend with a cat. Don't buy one to do this, though. Okay? Visit a second friend with a cat, cause your eyes itch, become sneezy. Theory. Experimental results indicate that indeed you're allergic to cats. You did that without even going to the doctor. You got it? So this is how we carry it through, and we use several examples there. And we'll perhaps do these, and we'll ask you the theory. And you want to read through this example and perhaps the example I just shared. Okay? All right? From each of these, indicate whether the step is a scientific method, describes an observation, hypothesis, experiment, or a theory. Okay? Here we go. Let's give it a try. And listen up, guys. I am less interested in you proving to me how brilliant you are. You are all brilliant. Okay? I now anoint you as brilliant. Okay? I give you the sword. Okay? Take you to the White House. Whatever it takes. You're brilliant. Please don't try to prove that to me just yet. Chime in, have guts, throw out an answer. You got it? All right? Here we go. Ready? And we'll see what happens. All right? All right. And we'll try it. And you can write on your paper if you want to, or you can say them out. A blender does not work when plugged in. Observation, hypothesis, experiment, theory. Anybody want to just say something out? Observation. Yeah, that's okay. I can buy that for now. I'll buy any of what you say right now, and then we'll see what we have, right? Okay, you said that because it kind of makes a little bit of sense. The blender motor is broken. That could be. It doesn't look like I did anything, right? It could be a theory, could be a hypothesis. And I want you to watch the ones we get most confused between is hypothesis and theory. Okay, and that's where it's so, okay. The plug has malfunction. Hypothesis. Okay. Theory. Yes, you said? Either one. So you're somewhere in between there, and you could be right on either one. And I just want you to think about it now without me just saying yes or no. Does everyone follow? Okay. And that's how I tend to be. Okay. I'll say I don't know. Okay. That's just my way of making sure you keep pushing and keep challenging. Okay. The blender does not work when plugged into another outlet. What's that? Yeah. Okay. Maybe it could be observation, right? Okay. The blender, probably not. But the blender needs repair. Hypothesis, theory, hypothesis, theory. Kind of deal with those. Let's take a look at what this author believes they to be. Yeah, there you go. Okay. The theory is it needs. Okay. So you start thinking about theory tends to drive you toward what you think should happen next, almost. You get it? All right. So notice here the plug has malfunction. That's a hypothesis. Okay. Okay. The hypothesis tends to be that first thought, although I can't say that. This is some people's first thought. The blender needs repairing. That's the first thing that'll go right to a theory. You need to fix it. Well, how do you know I need to fix it? It could not be that. Okay? The plug is malfunction. Okay? Or the blender motor is broken. Okay? This tends to deal with what's happening. This tends to deal with what needs to happen. One way of thinking about it, help you kind of differentiate those. These are two where most people tend to get them a little bit confused. Okay? So give that some thought, play around with it. All right? All right? Everybody good? All right. Because today we're going to cover a fair amount. We're going to cover 2 chapters today. All right? And we will take some breaks. All right? So we're going to start playing now with some math skills. Now, when we do these math skills, I will apologize to those of you who already know this, okay? All right, if you decide to take a nap, I wish you wouldn't, while I go through this, then I won't argue with you, but I expect to see the results on there. Please don't take a nap, though, okay? All right, but so we will go through these to be sure that you're exposed to them. Now, again, please don't feel pressure to impress me that you remember all of this or don't remember it. I will go through it in detail. So, we'll start to talk about all these, right? Place values. It's 2,518. Okay? So we are familiar with thousands. It's kind of a general. Hundreds. Count your money. Usually we can do these, right? You know a 10 spot, right? And these are ones that the waitresses hate to see coming, right? The ones, you know, okay? You know, you brought in 20 people, right? And all you saw were 2 ones on the table, right? Yeah. This is what the waitresses, right? The ones. Does everyone know these? Okay, good. So we won't belabor this. In terms of decimals, how are they on decimals? We know the ones, tenths is first place in the decimals. We know the hundredths for the most part. Pretty much, I'm kind of saying in general, yes. So we won't spend much time on this. Okay, just want to be familiar with it. These tens, ones, tenth, hundreds, thousands. Okay, all right. We all know what a positive number is. We know a negative number. Again, I apologize. I'm not trying to insult you. This is part of the curriculum. Okay. We know how to do this. Basic multiplication. We do understand 2 negatives make a positive. Okay, everywhere except in life, right? Okay, so we do understand that. We do a negative and positive makes it negative. And we know how to do that. We know how to do basic division. Okay, because you will be doing these operations. And if you don't, please, again, I'm not insulting you. And you say, well, maybe you should know that we're in college. It is in your textbook, and we want to make sure we at least brought it to your attention. Okay. But I'm not going to spend any time on it unless we have to. We do know how to do these operations. If you don't, make sure you ask me while we're doing them, playing around today with problems. Positive number, negative, we do know how to do this, right? You take the difference. Okay. If you don't, punch it in your calculator. If it really kind of gets you, go ahead and punch it. Most of the numbers that I'll give you can be done in your fingers and toes in your head, or borrow your friend's toes. Okay? All right? I care more about the operation than you knowing how to do huge numbers or whatever. These are other examples. Percentages, very important. Let's talk about percentages. Percentages are always the part over the whole. I don't care what happens the rest of the semester. Any percent. Now, here's the thing. You generally know that, right? And you generally think like that, but when it comes to science, we tend to just kind of really fall out and, wow, what's going to happen? It's the same thing. For example, how many people do we have in this classroom? 2, 4, 5, 10, 12? I think I did that right. If we assume anatomical females, and I apologize if I'm incorrectly in that assumption assignment, it's not meant to be that way, but if we assume anatomical females, we'd say 2, 4, 6, 8, 10, 11 out of total, how many of you? 5, 10, 12. That can't be right then. 5, 6, 7, 8, 9, 10. Yeah. So we have a total count of what, 12? And females would be what, 10? There you go. That's your percent. Times 100. What's times 100? That's your percent. Males would be what? 2 over 12. Okay. Watch this. If I told you, this is carbon dioxide. I calculated. I'm not asleep. 3, 2, 3, 4. If I told you that carbon dioxide has what's called a molar mass of 44. I told you that. And asked you what the percent, and I told you that of this carbon is 12, this is 16, this is 16. Could you tell me the percent carbon in that? The answer to that would be what? Yes. The answer is yes. There you go. You know why? Because you're going to treat it just like you just did the males and females in the room. You get it? You're going to always treat your percentages the same way. Don't let the chemistry go, oh, it's chemistry now. You're going to treat it the same way. So what if I told you there's 44 people in the room? Right? And there were 12 of them were sitting there with blue hats on. You'd say, oh, blue hats would be 12 divided by 44. Wouldn't you? Right? That's exactly what you do. So treat it as people sitting in the room. Treat it as vehicles in the parking lot. Treat it as chairs in your house. You get it? 44 units of carbon dioxide. I told you 12 of them are carbon, so I said 12 divided by 44 is that. So what if I told you, what would be oxygen? I told you this is 16 and 16. So how many oxygen altogether? 32, right. So you're doing it in your head already. And this is how we'll do it. You know it's 32, so it's 32 over what? How many were in the room? 44. Times 100. You're done. This is how you do percentages. And you're going to do the percentage the rest of the semester. Follow? That's how you do it. You treat it as people sitting in the room. Don't let it, because it's chemistry, frighten you. Okay? So everyone follow. Okay, let's see if you got it. Let's tell you this is water. H2O. This is its composition. This is how we write its composition. This is its structure. It's called a bent structure. And I told you that I looked up, and I was really smart, and I found out that it was 18. And that's 18 grams per mole. Do you care what the units are? Do you really care? No. You know it's 18. You get it? It's 18 grams per mole. 18 molar mass. And I told you that hydrogen is 1 and oxygen is 16. And I asked you percent oxygen in water, what would you do? Times? What if I told you water? Thank you. What if I told you hydrogen? What would you do? There you go. You notice how you did all that in your head? That's what you're going to be able to do. Okay? You get the concept? So any percentages that we do, absolutely any, I don't care what it is. Okay? Treat it as people in the classroom. I don't care what the percentage, just count the units. Count the numbers. Okay? And you notice how right away you knew you had 1 and 1 there? Someone will be asking, what do I do with this 2? They have 2 of them. What do you care? You got it? They happen to be 1. You get it? So everyone follow. This is how you'll do percentages over and over again. All right? Questions? Yeah.
Maybe a dumb question.
It's not for me.
Would you want us to do percentages? You're not going to mark us down if we don't reduce at any point of it?
If you reduce, you're going to always punch out a number.
Okay.
You're going to punch down a value.
Okay.
Because you're doing ratios.
I know, that's why I wanted to ask.
Yep. So what you do, you take your ratio times 100. That's what you're actually doing.
Right.
Yep. And so, no. So the answer question reduce down, no. So instead of saying 16 over 18, no. Why? In chemistry, it's smarter not to reduce. There's one place in chemistry you'll learn to reduce. It's going to be called empirical formula. But in chemistry, it's smart to simply write the values. Don't try to do any fancy math. Say, well, 16 over 18, everybody knows that's 2 over 4 or something, whatever it is. What is it? Something, whatever. 2 and then 16, whatever it comes out to. Got it?
I've been sure
8 over 9.
I've lost points and stuff like that before. I just wanted
You won't lose points here with it. So the answer is no. It's smarter to simply give me the values. And what's that, 8 over 9? Is that right? I think I get it right. Yeah, see, I can't even do it. All right? You follow? No. In chemistry, don't reduce. It's smarter. Okay? When you work, particularly in my class, don't reduce. It's smarter not to reduce. That would track absolutely everything we got and where we got it from. Okay? So don't be over fancy, and you'd be wise to do that if you're in the medical profession and those types of. Reduction is just something we teach you in elementary school so you can know that they're common. Okay? But no. Good question. All right? So now you know how to do percentages. That's how we do them. So what happened here? Now you can read the example, right? An aspirin contains 325 milligrams of aspirin. Okay, that's the active ingredient, right? But the total mass of the aspirin is 545. You could have done this one. Now you get it, right? The total is that. The part is that. Okay? So I can ask you the question then, how much of that, so that's percent of active, right? Does everyone understand that? Now watch. You can do this. What's percent of inactive? Tell me how you do it.
100 minus active.
Say again?
100 minus active.
No, you would subtract.
That's one way.
Yeah.
Who said this, that? Yeah, 100 minus active. That's one way. That's one way. Very good. This is follow he just did.
Yeah.
He said knows it has to be 100, right? So he's going to say 100. I'm sorry.
I was going to say, is this where the conversion factors come in?
See, now you're thinking really conversion factors and all that really super stuff that you may or may not need. You get it? See. We'll talk about that later, by the way. Thanks for asking that. But you may or may not need this fancy conversion factor. Right? And see, here's where you're going to get in my class. Here's where you're going to discover. We don't memorize anything. We don't memorize any steps, any processes. We just do them. We do whatever we need to do and use whatever we need to use. So let's use yours first. He said, well, I know it's 100, so I'm going to do it that way. I'm going to say 100 minus 56.6. Is that what you're doing?
59.6.
Well, who's picking on me? You'll find. And someone's always got to run the numbers for me, by the way, because I never do them. Okay? There's a 4. Anybody got it already? Let's see, what again? 40?
40.4.
Okay, good. All right. So so if I say run the numbers, just run the numbers. Trust me, you don't want me punching numbers. I have fat fingers. Okay? Okay? And most of it I try to do in my head. That's one way, and somebody else had another way. Where are you going?
Well, I would just subtract the 325 from 545 to get my inactive.
There you go. What did I get the right number?
325. Yeah.
Here?
Nope. You're.
I'm okay.
545, and then the below is 325. Okay.
Yeah. And so we take what, 120 over?
545
So you guys know how to do it. That's what I wanted to know.
times.
Yeah. By the way, a conversion factor is a simple way of saying a ratio. That's all conversion factors are. They're ratios. In this case, we're staying within the set. Therefore, we don't need a new ratio to do it. Okay. We're just aspirin to aspirin. You get it? So that's what a conversion factor is. Okay, that's why I want to come back to it once we finish there. Got it? I'll do that occasionally, by the way. I'll hear you, and I'll finish a train of thought, then I'll come back to you. Does everyone follow? So I'm not ignoring you. Okay? But yeah. But we don't need to use the conversion factor here because we're within the set. If we're
I suck at remembering what those mean.
so I'm sorry.
I said that's good because I suck at remembering what those mean.
Okay, so here we got it. Everybody know how to do percentages now? This is how you would do them over and over again. Okay? Don't sweat it when you go from one material to the other. Treat it as students sitting in the classroom. Don't make it any more complicated than that. Don't try to reduce it. Don't try to interconvert it. Got it? Okay. So that's how we do percentages. Any questions? You guys are good on percentages then? Because you will do these over and over again. Okay? Very good. Let's see what we have next. I don't remember. Let's see, we're on time. I'm going to try to finish these. 5% red balls. That's 5 out of 100. You know that, right? Now you know 50% green balls. So if they tell you the percent, so if I told you it was 32% active, you'd say, okay, 32 over 100. What's so deep about that? Get it? I told you it was 4% active, you say, okay, you said that was 4 over 100. You get it? Does everyone follow? Okay? Does everyone get how that works? That's all you do. It is no more complicated than that. And someone said, well, gee, why do we complicate it? Well, we have an academic responsibility to make sure we go through all the intricate details. But in the end, it's really straightforward, okay? And I teach it in that fashion, okay? Let's see what we have here. Rearranging equations. Okay. I'm going to walk through this, and I'm going to assume that you probably can do some of this. But in the cases where you can't, you will see me do them as we go through the course. You follow? Okay? So I'm going to walk through this with the assumption that you can do some of this, and if you can't, you'll ask me and I'll show you how to rearrange, and I can show you by way of some tutor notes that makes it really, really simple. I don't know if I have a video on it yet or not. Maybe I'll post one. Okay? So here, this is rearrangement equations. When it's added, you simply subtract it, you walk through, and you divide. So recall that kind of somewhat. Okay? Has anyone been out of high school math over 4 years? Okay, all right. Then we'll walk through some of this. Okay, and we'll, as we go, we'll math after about 4 years. If you don't use it, it really goes like this. It kind of falls off the map, right? Because you don't use it. It's not anything against you. It's just life. So don't sweat it. We'll walk you through it. So I'm just going to go through these, but when we have to use these, I will show you step by step. You will not have one math problem on any of my exams that I will not have shown you how to walk through. Does everyone follow? Not a one. There will not be one. Okay. All right. So here we kind of go through and check the answers. So take a look at these. Let's do, this is how we find temperature degrees. But we have a handout that we're going to walk through and work these. Okay. And when we do these, I'll show you on the board how to rearrange these equations. Again, this is a worksheet that we'll work through. This again is showing you that, and we'll show you how to solve all of these that we have to solve when we get to the gas laws. I will show you how to do these. But today I just want to introduce the concepts and have you start to refresh yourself. If you want, just go out to YouTube, find a good YouTube. There's some good ones and there's some very bad ones that will walk you through this. Okay. I don't have a YouTube on this, but I do have a site that has these on them, but they're paid downloads. They're like $2 or something like that, somewhere out there, called Kim Tutor Now. It has a lot of these examples on it. That's not a pro bono promote site, by the way, just an awareness. He's good. I like him already. You have to make the disclaimer, man. Come on, give me a break, right? Okay, there you go. Okay, this is something we want to be familiar with doing. And we'll do this and we're gonna finish this and then we're gonna take a break. Okay. Pace is still okay for you guys? Everybody still good? All right, this slide is really gonna help. Yep. How to read curves, and that's what I want you to get from this. Okay. Curves are no more than your GPS. That's what they are. This is your GPS. This is what your GPS app does. Okay? All right? And this is what used to happen when people travel. They would pull out a big map and they would go here to here to find the coordinates. Okay? Now it's all on your GPS. You press it and it goes. So I'm going to show you, this is what happens when you press that button. If you want to get to this location, the app says you have to go 50 this way, go up until you hit the diagonal, and go left. And it's read off each of these. We read this side. Don't look at it as chemistry. You're going north and south, east and west. Okay, no, you don't know your north and south, east and west. Okay, you're going... You're headed up to Mackinac, You're headed to Ann Arbor, okay? You're going over to Mount Pleasant, or you're going over to Bay City. Got it? It's just simply coordinates. Don't look at it as anything different. Read it that way. Here on the volume. So here on the volume, we have the volume on this axis. We have temperature on this axis. Means that we would have one set of coordinates here on what's called the y. We have one set of coordinates here on the x. Okay, so this is your x, y that you've been seeing in math. X, comma, y. Okay? On the x-axis on temperature, the question would be, what volume of the balloon, at what volume would the balloon be if the temperature was 50 degrees C? So I simply drive over to in the Bay City direction on my x-axis. I go in the east direction here, over to 50. I stop at 50 and I go up to where it intersects the line. Once I get here, I simply draw straight edge over to here and I read. I don't do any math at all, I simply read. This is how you read graphs over and over again. Does everyone follow that? Okay. So someone please help me, and you can approximate it. If my temperature was 80 degrees C, what would be the volume of the balloon? 29. You know it's more than 28, right? Very good. That means you read it. How'd you read it? You went here, you went up, hit the line, you went here. If my temperature is 20 degrees, can I get 30 liters of volume in my balloon?
No.
You get it? That's how you read it. How much can I expect?
24.
How much? 24? You get it? That means you know how to read them. Does everyone follow? That's what you do. You simply read it. Don't pull out your calculator. Don't try to memorize. It's a graph. When it's a graph, just simply read the graph. It's your app. And your app requires 2 buttons. Click, click, and you're there. Get it? Okay. At 100 degrees C, what do you think? What's my volume going to look like approximately? About 30, over 30, right? You get it? That's how we read. Okay? Very good. You get it. Let's take a look at this one. A nurse administered Tylenol to lower child's fever. The graph shows the body temperature of the child plotted against time. So we have the body temperature. This is degrees C, by the way. Normal temperature is about a little less than 40 degrees C for your normal body temperature. If it's warm, it's above 40, by the way. That's kind of weird. If you touch something and you can feel it warm, you can assume it's above 40 degrees C. If you go, it's above 100. Get it? Okay? So if you touch it and you feel it, it's usually above. Okay? Because that's heat flow. Heat flows, not temperature. Heat flows from warm to cold. You get it? Okay. It flows from warm to cold. So let's say, for example, time after Tylenol given. So let's say her body temperature is 37. What are we going to get there? What's the time? 37.8. Yeah, 10 minutes. That means you can read it. Okay. Does everyone see why we got that? Everybody kind of, somewhat? Okay. Here to here and down. 34, we go here and down, here and down. So there we go. So about 10 minutes to get that. Okay. Does everyone follow? Right. So what's measured on the vertical axis here? Very good. In what units? Very good. You get it then. What is the range of the value of the vertical axis? How far can we go? What's the range? 37 to 90, right? To 39, right? Yeah. So we don't measure outside of that with this graph, right? Very good. What's measured on the horizontal? Time. Very good. Time in minutes. Very good. What is the range? Very good. You guys can read graphs. We're going to break now, and we're going to do we'll come back. I think we may go to the next chapter. We're going to do all the scientific notation on the sheets. So let's break for a bit. Back in 5. Does 5 work for you guys? Okay, thanks.